Okay, thanks, Jeff. Actually, I'm not going to start with that. I'll start with this. I'm not sure if this has been shown before, because unfortunately I wasn't here for the last few days. Can you hear me? I've got this horrendous cold. Good. And this is from 1991, and it's one of my favourite photographs, actually, because it was the meeting I first met Helmut. I think you can see him there. He's also on here. I don't know who he's talking to. There's Peter Shook and two young men at the back there. Not quite so young. Yeah, there's Ariel Lustig. Remember Ariel? Yeah, he used to be a frequent guy at these meetings. And Helmut was doing a PhD then with, where are we? Walter Borchardt. And actually did a lot of work behind that meeting. And after that, for some unknown reason, he wants to come and join us at Nottingham as a postdoc. He showed us his PhD, all in German, about centrifugation of gels, but looked pretty good stuff. And so yeah, we took him on. And in fact, they were some of the most productive years. The work with Owen possibly accepted. Anybody else? We had with the ncmh, because Don Windsor was at the same time as a visiting fellow. It's actually nice. There's a poster on the Schlieren thing at the back there, which refers to some of the earlier work with Helmut. Great guy. Anyway, when he finished with me, he went on to do. He got a job at the Max Planck Institute in Potsdam with Antonetti, and then went on from great things from there. And then last year, sorry, Alwyn, I didn't go. Sorry, Trusha. I know he's not here. I didn't go, but my postdoc, Vlad, went. And he got this picture of the three of them with this little caption. We're missing you, Steve. You should be here. And of course, I'm ever so sorry. Yeah, sorry, Helmut. But at least I'm here now. Yeah, great picture, great guy, and it's a great loss to the field. And very highly appropriate they have this award now, which is dedicated to him. Still can't get my head around the fact that he's gone. Anyway. Right, so hydrodynamic tools for assessing the molecular integrity of archaeological consultants, the Saving Oseberg project. And actually my PhD student, Jennifer, later postdoc, has spoken once or twice at these meetings about this sort of stuff. This is my turn. And this is something we've been working on for the last 9 years, and how polymers and understanding the hydrodynamic properties of these polymers used to consolidate crumbling away archaeological material, like some of the artifacts that are associated with the Oseberg ship in Norway, and how we can use natural products, for example, polymers, a polymer called chitosan from this little rascal here, to try and rescue the situation. So it started in 2015 when the Viking ship museum curator, Jan Bill, convened a meeting of polymer scientists, chemists, conservators to try and address the problem. The problem wasn't so much with the big Viking ships themselves, the Oseberg, the Ton ship, the Gokstad ship, but the artifacts, the beautiful burial artifacts that were buried with them, because they were treated with a material called alum. These are the artifacts. Some are more degraded compared to the other. This sledge at the bottom is particularly degraded and at the point of collapsing. Now, when these ships were dug up with all the artifacts over 100 years ago, they were treated with this material called alum, hot alum, which forms very strong crystals, and then that stops the dehydrated wood from cracking as it dries out, so it maintains the structure. But over the years, unfortunately, the alum has turned to sulfuric acid, which is not good from a conservation point of view. So a lot of the cellulose and also some of the lignin has rotted away in many of these objects. And if you look inside, you can see that how rotten they are. So the object is really to design a toolbox of consolidants depending on the state of severity, not just for the Oseberg, but for other archaeological wood, trying to avoid petrochemical-based formulations, which is what's used, for example, for the Murray rose. There's also problems with that, viscoelastic creep and other things, degradation through interaction with iron rivets and things. So there's two classes we've been developing. Class 1, which are aqueous formulations, soluble in aqueous solutions, chitosans, aminocelluloses, and more lately terpene derivatives. And then class 2, which is catering for the Oseberg, really, because we don't want to destroy the alum which is remaining by putting in aqueous stuff. So with these, we're after non-aqueous formulations involving derivatized chitosans, these wonderful molecules called aminocelluloses, lignans, terpenes, and siloxanes. There's also class 3, which involves consolidation of the Oseberg tapestries, but I'm not going to talk about that now. Maybe Jennifer can do that at the next meeting. So these consolidants should be soluble, low viscosity resins, easy to inject, natural products, bio-based, molecular weight for infusion, about 4 kilodaltons, otherwise they won't go in. And then they'll cure inside the object, interacting with the remaining material to give a strong network, of course non-toxic, only nasties being given off in the museums. So the first point of call, chitosans, which come from the shells of, well, it's chitin. And chitosan is modified chitin. So it's basically a cellulose structure with these functional groups here, which can be acetylated or not. Acetylated gives a hydrophobic sort of molecule. Deacetylated, you get this charged, gives a hydrophilic molecule. So you can control the degree of acetylation to give different sorts of properties, but the backbone is similar to cellulose. So the first thing we did, this is interesting hydrodynamics we can get involved with here, is to look at the stiffness of these polymers, because you want something which is not very flexible, something which is stiff or extended. And from AFM, you can see that they looks like a stiffy sort of molecule. The Mark-Howing coefficient from viscosity, again, corresponds to this. And using Jose's hide-fit routine, which he'll be talking about tomorrow, the latest version of it, which combines data sets of viscosity, RG, and sedimentation coefficient versus molecular weight to give you sort of minimize a target function. All this data corresponds to a semi-flexible extended molecule, which is what we want to interact with the surviving wood material. Now, in terms of molecular weights, these are usually too large when they're extracted. We determine the molecular weights here using this extended Fujita method we developed about 15 years ago with Peter Schuck, extending a method for Fujita for random coils to cater for different conformations. And these are the distributions, the transformations from the geovespots, again, too big. But you can degrade them in a controllable sort of way with UV and hydrogen peroxide to give the molecular weights that you want, which is what we did. Right. Now, one problem with chitosans is they're a bit variable in terms of their properties because of the variation in degrees of acetylation and things. So they're not as reproducible as we would wish. However, we can get these synthetic bio-inspired, bio-based still, reproducible alternatives to chitosands called amino celluloses, which still possess the favorable properties of chitosands. And that's working with Thomas Heitzer at the University of Jena. So you've got your beta-1,4 glucan backbone with these amino groups coming off, primary, secondary amines, and these benzoyl groups coming off as well. Almost looks like a protein, except that the bonds are glycosidic. But we just looked at them in the C of S plot, and when you first see this sort of thing, first of all, you question the software. Is there a fault with Peter's software somewhere? But no, these were genuine sort of multi-peak peaks coming out, which you've never seen before for polysaccharides. And they seem to follow a S to the power m 2/3 trend. And that was independent. We tried different aminocelluloses with different side groups coming off, and they all gave these effects. Now, in fact, you plot the whole lot on log S against log M, it all comes out to be m to the power 2/3, which is what you get for globular proteins. Strange, very strange. So we published this in Angewandte Chemie, protein-like oligomerization of carbohydrates. One of these nice things. But that's a potential advantage in terms of consolidation, because if these things will self-associate, self-assemble inside the wood once you've injected it, then that's a big bonus. The assembly is reversible. These are the characteristic plots. This is from Rourke and Afantis way back in the 1960s. So when you get number and weight and Z averages all coming to the same value at zero concentration, that's a sign of a reversible interaction. And also, if you get overlap of points of point average molecular weight from sedimentation equilibrium, remember that? Yes. Again, this comes from Rourke and Afantis. That's a sign for self-association. Just an interest. These are some old plots from proteins. One null, one from Hancock and Williams, bottom left for chymotrypsinogen. And this one at the top was with Helmut. We did on the electron transfer protein. You can see the overlap across the concentration range. Where it doesn't happen is for mucins, where you get this non-overlap. Anyway, just a little methodological departure. Okay, so these are wonderful molecules. The next thing is, can we modify or improve them? Well, again, Jennifer gave a talk on these at, I think it was Christchurch, on enhancing the assembly process of aminocelluloses by changing one of the amines for a hydroxyl group. And also she did some work on chitosands to see if she could, by substitutions, by putting siloxane residues on, you could give them non-aqueous solubility. Indeed, these ones are soluble in toluene and ethanol. And when you inject them into the wood, you can see from both SEM and energy dispersive X-ray spectroscopy the thickening and also the distribution of, this is tuned for silicon here, coating the insides, the pores inside the wood. So that's promising. And you can test the wood. We don't just go straight in by injecting the stuff into the Oseberg artifacts. That would be a disaster, because you only get one chance with these things. So we do everything on test wood, either artificially aged wood or bits of archaeological wood which are not structural. So that's what we do. Only for dead shore will they go into these priceless objects and get it wrong. It's a disaster. Right, the next class, related classes, are lignans and terpenes. So lignans to replace the rotted ones, and terpenes, which have got a variety of wonderful properties. They're natural. They come from wood, for example, pine, the sap in pine, and they could be modified or tuned with different properties, and then polymerized to the appropriate molecular weight. Now, we had another PhD student, Michel Coutajar, who was working on that. And after this process, after polymerization, this is the first one we found was promising, TPA5, which was soluble in isopropanol, which is good because the conservators don't mind that. It's a pretty okay solvent compared to some other stuff needed to solubilize these things. And then we checked out the hydrodynamic properties of these. The molecular weight from sedimentation equilibrium came out to be about 4,500. Again, good. And there are not too many aggregates about, which is also good. And then from the shape, we used the old Schrager-Mandelkern beta function to see whether a prolate or oblate model would be the most appropriate. You can't get axial ratios from this function. It's too insensitive. So it was consistent with a prolate. And these are the various elongated shapes that we got for different plausible values of the swelling ratios. So that's all good. You want something, again, which is sort of not a tight ball, but something that's extended so it can interact with the things inside the surviving wood. Again, these are some other ones that Michel produced with different functional properties. Again, with the right sort of molecular weight ranges. Now, for lignans, for these flat shaped, these are more flat shaped, so the oblate models are more appropriate. And we looked at two types called soda and kraft. They refer to the sources which they come from. And all these F numbers mean the different types of extraction solvents where you can affect the shape and sizes of the lignin. So again, it's building the toolbox of materials which the conservator could use. And then finally, we're back to this seaside again. We started off with crabs, right? Not very impressed with that. But that was the sand, okay, like Mel's Beach, there I was brought up. But Mel's sand, of course, is rich in silicon dioxide. So you can make these siloxanes, which also looked like very promising consolidants. Again, we characterize them as before. I'm not going to go through all that. Actually, I'm ahead of time, can't believe it. You've got speakers who are ahead of time, the second one. And it's rather boring, isn't it? You do the shape determinations, and again, the same sort of, 4-to-1 ratio, 4,000 molecular weight, 4-to-1. But at least it's consistent. Yeah, which is not normally what you get with polymers and things and polysaccharides and things. So that's good news. Right, and with these actually, these are perhaps the most promising. So we've actually treated archaeological wood from the Oseberg, not actually from the Oseberg. We haven't snapped bits off and tried that out. These are bits that were found with the Oseberg when they were dug up all those years ago. And the top is before retreatment with this siloxane, in turpentine. These are the sort of concentrations that we inject with, the sort of resins that are injected. And this is after treatment. And you do all the strength tests and everything else, and do all the internal structural measurements as well. So this looks promising. So we're almost there, but it depends. It's horses for courses, because some of the not so badly degraded Oseberg objects we could use aqueous formulations and not have to use these non-aqueous ones. So again, it really is horses for courses. So soon the conservators are going to have to make a choice. The fact that they're scanning all their objects is probably a sign that they don't trust us just in case things go wrong, they can, make some 3D replicas. But I think we're getting quite close, because it's very difficult to correct once you get it wrong, like the alum. We've had to work around the alum. We can't just remove it because the whole thing would collapse. We've also had to treat the wood with de-acidifying agents like calcium hydroxide nanoparticles and things. But it's been an exciting project with exciting hydrodynamics. Anyway, this is just a brief glimpse. I'm not expecting you to read that, but I know this is being recorded. So those who, the one of you wants to replay this, then all the relevant publications are there, including 3 excellent PhD theses, and by Jennifer, Michelle. Yudong hasn't submitted hers yet. She was the one working on Lignans, but Emily has. So it's been teamwork involving a large number of people, polymer scientists working with conservators, such as Ellie Schofield, who's the chief conservator at the Mary Rose, and it's really been a fascinating project. You get trips to Norway and things. It's nice over there, and it's been refunded. We've had Saving Oseberg 3, it's called now, funded by the Norwegian Ministry of Education. So that's going to continue. And of course, thanks to Helmut, because some of the work that we've been describing here is based on some of the earlier work that Helmut did, with the ellipse programs and the M-star and all this sort of stuff. So a big thanks to the great man. And with that, I'll say ahead of time, thank you.